Now today, for our final presentation, it's a great pleasure for me to introduce to you Professor Michael Loui. Michael is Professor of Electrical and Computer Engineering and Research Professor in the Coordinated Science Laboratory here at the University of Illinois. He's also Associate Dean of the Graduate College. Michael was born in Philadelphia, Pennsylvania, and studied at Yale University and the Massachusetts Institute of Technology. His research interests include computational complexity theory, theory of parallel and distributed computation, and fault-tolerant software. And Michael is also one of the university's, I should say one of the nation's truly stellar teachers. He's won awards at the college, university, and even national level for teaching. Today, Michael has kindly agreed to give us a talk with a wonderful title, So You Thought Computers Could Do Anything? Some Provably Unsolvable and Infeasible Computational Problems. Please join me in welcoming Professor Michael Loui.
I'd like to thank Paul for inviting me to give this talk and for his very kind introduction. The computer is truly one of the miracles of the 20th century. Computers affect our lives daily. Whenever we make a telephone call, perform a banking transaction with an automated teller machine, or flying an airplane, computers are intimately involved. Computers make it possible services that were heretofore merely the stuff of fantasies. Today you can sit at home and using your computer so you can surf the World Wide Web and look at pictures in the National Gallery of Art. Computers are used for sending astronauts to the moon. One might think with all these successes that computers could really do anything. And indeed, in 1984, Time magazine wrote an article in which this statement appeared: put the right kind of software into a computer and it will do whatever you want it to. There may be limits on what you can do with the machines themselves, but there are no limits on what you can do with software. This is a very nice and stirring statement. Unfortunately, it's false. We will show that there are, in fact, problems that no computer program can solve. Now, many of you, I assume most of you have used computers at one time or another, and sometimes when you're using the computer, the screen suddenly freezes up as if nothing is happening. In reality, the computers are still working internally, executing instructions internally, but there's nothing happening on the output. And you can't tell whether the computer is slow or whether it's stuck in an infinite loop and would never halt. So we're going to look at some programs that sometimes halt and sometimes don't halt. And these are written in a way that I hope will be pretty clear. Here's a very simple program. The first step is to read in some input number. And then the second step is, while this variable x is not equal to 1, subtract 2 from x. And if you ever get to the point where the variable x has the value 1, you stop. So when the input value is 4, the first thing that happens is x is not 1, so you replace x by x minus 2, and the value of x becomes 2. When you go through the loop again, you replace x by x minus 2, you get 0, negative 2, negative 4, and so on. And so in principle, this program wouldn't halt. In practice, because of finite word size, it actually wraps around to some large positive number. But in fact, in practice, this program won't halt either. On the other hand, the program certainly does halt when the input value is a positive odd integer. For example, if the input value is 3, then x is initialized to 3. That's your input value. And then you subtract 2, the value becomes 1, and at that point, you stop. Now, this is a fairly easy program to analyze, and it's easy to tell when this program was going to halt. But this other program, which is just slightly more complicated, is much more difficult to analyze. Again, you input a value x. While the value of x is not equal to 1, you do the following. If x, the current value of x, is even, then divide it by 2. Otherwise, if the current value of x is odd, then replace x by 3x plus 1. So when the input value is 13, that's an odd number, so what happens is we replace x by 3x plus 1. 3 times 13 plus 1 is 40. And now you've got an even number, so you replace x by half of it. You get 20, 10, 5, because in each of those cases x was even. X is now odd, so 3x plus 1 becomes 16, And now when you divide in half successively, you go through the sequence 8, 4, 2, and 1. And at that point, x is 1, and now the program halts or stops. Does the program always halt for all possible inputs? Nobody knows. This I'll leave you as a puzzle for you to think about and take home. Now, how would you go about trying to figure out whether this program always halts? Well, you could try, or even whether it halts in a particular input. You could try running it, right? Well, if it runs and then it halts, you know it halts. But it could take a long time. You might get impatient. Your parents might say, come home and come to dinner, get off the computer. And really, it's very difficult to tell the difference between whether the program is just slow or whether it's completely stuck. So let me phrase it would be very nice if we had an automatic way of telling for a given program R and a given input X, an automatic way of telling whether the program R always halts, whether the program R halts on the input X. Ideally, we'd like to have this way so automatically and so precisely specified that we could write a program that would take two inputs, a program R and an input X, and tell us whether R halts on X. So it would say yes if R halts on X, and no if R does not halt on X. So it prints out yes or prints out no. Now, so this would be very, very nice in deciding whether our software is whether our software is working. Unfortunately, this is not possible. This problem is unsolvable. There is no program Q which takes any pair R and X, where R is a program and X is an input, and terminates within finite time with an output of yes if R halts on input X, a no if R does not halt on input X. So there is no way of solving this problem in general for all programs and all inputs. No matter how long you work on the halting problem, no matter how many helpers you get, graduate students do all the work around here, no matter how much research funding you have, it can't be done. You cannot write a program Q that will satisfy this specification. And this is one of the first results of computer science and engineering. It's due to Alan Turing, a British logician, in 1936. Turing is known for many other things, including cracking the German Enigma code in World War II and helped the Allies win the war. So I'd like to go through the proof that there is no solution to the halting problem. Suppose, to the contrary, such a program Q does exist. Suppose we could have a program Q that would solve the halting problem as stated over there. Well, I'm going to create a new program S, and S will do the following. S will take as input a program, the text of a program, right? We can write down the program as a text, and it will take that as an input. The first thing it will do is it will duplicate the text of the program W. So it will make two copies. That's very easy to do. And now we'll feed both W twice to this program that we thought existed, Q. Now, it may seem strange to ask whether the program W halts on an input of W, but remember, a program is just a sequence of symbols, a text of the program. So you can think of asking Q, does the program W halt if given as input the text of W? Seems like a strange thing to do, but this is this will lead to a contradiction. When Q terminates, we assume that Q will terminate. It will answer either yes, W will halt on input W, or no, W will not halt when given input W. At that point, our program S will do the following. If Q says yes, then our program S that we're defining will enter an infinite loop, right? We've seen an example where you could just go around forever and not do anything. So it will not halt. On the other hand, once Q says no, my program S is going to halt. So let me just write that down, or state that again here. If the program W halts on an input of W, then Q is going to output yes. And then, according to the construction here, S is going to enter an infinite loop. It will just keep running forever. On the other hand, if the program W does not halt when the input is the text of W, then Q outputs no, and S halts. So that's exactly what happens here. Now, what happens? Now, this is a perfectly good program. We said that Q was a program. We assumed that Q existed. And all we've done is made these very minor modifications. So S is a perfectly legitimate program in itself. What happens if we give S as input the text of S? So it's as if we're giving S as its input the program S. Okay, so what it does is it duplicates S, right? It makes a copy, and it feeds both to Q, and we ask Q, does the program S halt when given S as an input? Okay, Q is going to answer either yes or no. If Q answers yes, then according to our construction, S will enter an infinite loop and not halt. On the other hand, if Q answers no, then S halts. Now, let's think about this. On this branch, if Q answered yes, then on input S, the program S halts. But we just, by construction, S is not going to halt. See? If Q answered yes, then in fact, S does not halt. So it must not, there's something wrong here. Right? S cannot halt on S because, in fact, it doesn't halt. So that can't possibly happen. On the other hand, Q could answer no. And the answer no says that on input S, the program S does not halt. But then, of course, it halts. So that's a contradiction, too. Really strange, isn't it? Let's think about this. So if S halts on S, if Q says S halts on S, then S doesn't halt. If Q says S does not halt on S, then S halts. Is this a joke? No, in fact, it's a mathematically rigorous proof that, well, in each case, we got a contradiction. So where did we go wrong? Everything is, in fact, perfectly fine, except our original assumption. Our original assumption was that Q existed. So that must be wrong. And the only reasonable conclusion is that this program Q does not, in fact, exist. So there is no way of solving the halting problem. There is no program Q that, given an input of a program and another input, will solve the halting problem. Any question about that? So if we divide our space of computational problems up, we now know that there are some unsolvable problems, such as the halting problem is an example of that. And then, of course, there's some other problems that are solvable, but we'll take a look at those later. We'll divide those. We'll show more structure among the ones that are solvable later. Well, you might ask, is this an anomaly? Is this, I mean, most problems are solvable. This must be a singular event. Is this an anomaly? In fact, there are many, many unsolvable problems. And this is a good excuse for me to give in to temptation and tell you about some of my own research. So this is a shameless advertisement for some of my research on impossibility results. Okay. This is a problem called the agreement problem. And this is a really fundamental problem whenever you have parallel or distributed computation. In this problem, we have a group of processors, right? You can think of them as small computers that communicate by reading and writing values in a shared memory. You have seen advertisements for computers. They tell you how much RAM there is, how much random access memory there is. So that's the kind of memory that a computer uses. You can read and write values in a shared memory. And in this problem, each processor starts with an input, which could be 1 or 0. And at the end of executing some program, you want the processors to come up to agree on an output. They should either all agree on 0, as in this first line, or all agree on 1. Okay, that's why it's called the agreement problem. You want, by the end, all the processors to agree on one of the inputs. The rules here say you can't just always produce output 0 or always produce output 1, because that would be unfair. I mean, there would be nothing to do. So in this case, the output value must be one of the inputs. Now, this is kind of an abstract problem, but it arises in many, many cases. For example, when you have a distributed database, you are making updates to multiple copies of the database, and you want to enter the same information in all these different places. So but something might have gone wrong at one of the sites. So each site decides whether it wants to commit to a new value or abort the transaction, and you want them all to agree to commit to a new value or all to abort. So this is, I mean, this kind of agreement problem arises in many, many contexts in computing. Unfortunately, this problem can't be solved either. There is no program that solves the agreement problem. In the particular case when processors communicate asynchronously, that is, they read and write values whenever they like, and not all together at regular intervals, so they aren't synchronized. And processors can fail by stopping. Even only one processor could fail by stopping, and this is enough to make the agreement problem impossible to solve. So we'd like to solve this agreement problem in a fault-tolerant way when processors could fail, fail by stopping. And whenever you have computers using aircraft or banking, we want those to be fault-tolerant kinds of computer systems. So this is an example of a problem in fault-tolerant computing that simply cannot be solved. There is no way of solving the agreement problem in this case. Before I go on with some other kinds of computational problems, let me distinguish between algorithms and programs. So far I've been talking about programs. We want to avoid talking about programs that are in specific programming languages and talk about the methods used by the programs independent of whatever programming language you're using. So we want to make sure that our results don't depend on the particular programming language that you use. And so I want to, for the rest of the talk, I want to talk about algorithms. Now, an algorithm is basically a method or a recipe for doing something, for processing information independently of the programming language in which it's expressed. So an algorithm is a complete, precisely specified procedure for processing information. By processing information, we mean transforming it, making, such as doing addition, subtraction, arithmetic operations, transmitting information or communicating information from one place to another, storing or retrieving information. So algorithms are like recipes for doing things with information. A program is an expression of an algorithm in a particular programming language. I assume some of you have written programs in BASIC or Fortran or Pascal. There's some modern programming languages, C++, Java, and so on. There are hundreds of programming languages. And I'm going to talk about algorithms. So independent of whatever programming language you use, we'll talk about whether a problem can be solved. An analogy here is the same recipe for chocolate cake. I assume everybody here likes chocolate cake. Can be expressed in English and in Russian, although probably in Russian it might not be exactly the same thing. But the idea is that it's supposed to be the same recipe can be expressed in several different languages. So henceforth, I'm going to talk about algorithms. Now, let's look at another computational problem. And it will turn out that this is a fairly difficult problem to solve, even though it can be solved in principle. It's called the roadblock problem. The roadblock problem is a problem it's about a game between two players, and we'll call them A and B. And on each turn, actually I'll use this picture here. Oops. So on each turn, a player may move a car from one intersection to another along roads of the same color, and for that turn, provided that all intersections during the move are not occupied by other cars, they're free of other cars, and eventually you want to move a car to an intersection marked A wins or B wins. A tries to move a car to an intersection marked A wins, and B tries to move a car to where B wins. And here's an example. The duplication here, we've got roads that are black. So here are some black roads. Red roads, this one's red, and this one's red, and the other ones here are pink. So it's kind of hard to distinguish them. So we've got two kinds of cars. We've got Bugatti sports cars. There's one here, and a motorcycle here, and a motorcycle here. And so the Bugatti here, here's an intersection marked motorcycle wins. This one says Bugatti wins. So if we, say it's the player moving the Bugattis has the turn to move, the Bugatti player could move a car from T to U, and so that on the next turn, the Bugatti player can move that car from U down to V, where it says Bugatti wins. So that could be the first move, moving this car up to intersection U. Now, the motorcycle player could counter by moving the motorcycle from W to X, and that blocks the Bugatti player from moving down on this black road. But then in that case, the Bugatti player could move the Bugatti from Y to Z to this other intersection marked Bugatti wins. So if the Bugatti player moves first, then that player has an unbeatable strategy. And we'd like to know, does say the first player always have a winning strategy? And this is kind of a funny game, but you can certainly imagine other kinds of games that you're playing against opponents where you'd like to know, from this particular situation, does the first player have a winning strategy, given an initial configuration or placement of cars? Now, there are many, many configurations of this game. You could have up to n cars, if n is the number of intersections, and each of those cars could be at one of the other intersections. So there could be as something like n to the n configurations. Now, we'll show on subsequent slides that this can actually be a fairly large number. But nevertheless, this is a finite number. So there's a finite number of ways of placing all the cars. There are finitely many ways of playing the game that don't repeat configurations. So there are really only finitely many ways that the game can proceed. And so one can determine, in principle, whether the first player has a winning strategy. That is, a winning strategy says there exists a move for A such that for any way that B could counter the move for A, there exists a move for A, and so on. So we'd like to ask, since this is a large number, maybe there's a more clever way of solving this problem. Maybe there's a more clever way of determining whether the first player has a winning strategy. I'll let you think about that for a moment. Let me look at another, perhaps more practical computational problem, the traveling salesman problem, or at least it was called the traveling salesman problem when it was first formulated. Nowadays, in view of gender correctness, it's called the traveling salesperson problem. Say you're a traveling salesperson, you have to visit all these cities in Illinois and St. Louis. So you have to visit Champaign-Urbana and Chicago, Rockford, Peoria, Springfield, Bloomington Normal, Decatur, and St. Louis. And you want to have a tour of these cities that minimizes the total distance traveled. So you want to visit all of them exactly once and come back to the origin and minimize the total mileage. Or maybe, since you're short of time, maybe you want to minimize the total time. So here I've just written between every pair of cities that's connected by an interstate, the total number of miles that are involved, except, of course, from Peoria to Rockford, you can't go directly on an interstate. And this is a pretty good tour. From Champaign-Urbana, I can go to St. Louis, traveling 182 miles, then to Springfield for 100 miles, then to Decatur, another 39 miles, to Bloomington Normal, traveling 45 miles, to Peoria, 40 miles, to Rockford, 138 miles, to Chicago, 83, and then back to Champaign-Urbana, 137 miles. And the total length of the tour would be 764 miles. So we'd like to be able to solve this problem, especially if you're that poor traveling salesman who has to try to sell things and visit all these cities, minimizing the total distance traveled. Now, this is a fairly important problem. Let me look at the applications here. There are many applications here. For example, programming industrial robots. You might have a robot that has to visit several places in a flexible manufacturing plant. It has to go from this station to this station to this station. But maybe it doesn't have to do it in a particular order. It just has to visit all these stations. And you want to be efficient as efficient as possible, so you want to minimize the total distance traveled. Drilling holes in printed circuit boards. Because you have maybe one drill, you have to move to different places where the holes should be drilled, and you want to minimize the total time, which is related to the total distance. Or plotting points on large maps. Cartographers have to do this. There's one plotting pen, and you have to put many different points down on this map. So the number of cities here might be in the hundreds for a single map. Now, well, how would we solve this traveling salesman problem? Well, I could look at all the possible tours. how many possible tours are there? There are n places to start. And then after you choose your starting place, there are n-1 possible first cities to visit, then n-2, and so on, and then down to 1. So this is n factorial. And this is approximately, this is a good approximation to it, square root of 2 pi n times the quantity n over e to the n, where e is Euler's constant, it's about 2.7. So it also sort of behaves like n to the n. Again, the total number of possible tours is finite. You could just list them all, find out how long each of them is, and choose the shortest one, right? No problem. Well, there's a problem here. N factorial grows pretty fast, so it might take actually a long time to list all of those. Well, how long might it take? Well, let's take a look at some possible running times of some of these sort of exhaustive strategies. Let's assume that we can look at one possibility. I'll just leave that up. Let's assume we can look at one possibility every microsecond. So we can look at 1,000,000 possibilities per second. And this is fairly reasonable for computers today. You know that computers can usually take steps, often 1 billion steps in a second, but it might take a thousand of those steps to evaluate one of these tours. So this is sort of a reasonable ballpark figure for, we're going to give some ballpark figures for how long it might take to solve some of these hard problems. Now, the first three of these functions of n are n squared, and n cubed. So what I'm saying here for various values of n, how long we're talking about a computer taking if we do one of these possibilities in every microsecond. So here, if n is 10, then that's 10 microseconds to go through all these possibilities, and that's 0.00001 second, which you would not even notice, right? If it took that much time, that's less than a blink of an eye. Or even up here at n equal 40, this is a fraction of a second here, 0.064 seconds. You wouldn't even notice how long it took a computer if it took that long to solve your problem. On the other hand, when we move from these polynomials, n squared, n cubed, and so on, to these exponentials, 2 to the n, 3 to the n, things start growing pretty fast. For example, if we're talking about, if your algorithm took an amount of time that's something like 3 to the n, and if n was 30, you would take 6.5 years at 1 microsecond per possibility. So, and of course, if n is 40, it might take 3,885 centuries, which is a long time to wait. Even for some of you. Even if you're very patient, it would take a long time. Computers would probably really evolve a lot in 3,885 centuries. So, it's really not practical to use an algorithm that has this kind of running time for any reasonable size. Now, notice that, well, computers are getting faster every year, right? If we had a computer 10 times as fast in this lower right corner, we'd solve the problem in 388.5 centuries. Wow, this is a big improvement. Or maybe we should, we'll have computers maybe 100 times as fast in a decade or two. Well, then, only 38 centuries. But that's still too long, I think. Well, these are some functions. What about those? We've seen n factorial and n to the n. They grow even faster, or computers would take even more time. Okay? So let's, the traveling salesman problem, I'll just leave this here for comparison. For the traveling salesman problem, we talked about enumerating all of those n factorial possible tours, right? Well, if you're talking about a problem with only 10 cities, that's fairly easy. You could do that in just a matter of seconds. But on the other hand, if n is 20, right, if you're trying to solve a traveling salesman problem with 20 cities, looking at each tour, looking at 1,000,000 possible tours per second, it would take you 77,146 years, more or less. And if your computer was 10 times faster, so maybe I'm off by a factor of 10 in figuring out how fast your computer runs. Maybe you're really an ace programmer. You can make this program run 10 times faster than I thought. It would take you only 7,000 years. You probably don't want to wait that long. Well, if your algorithm was looked at n to the n possibilities, so we were looking at, say, the roadblock problem, this is 3 times 10 to the 12th is 3 billion years, which is of the same order of magnitude as the amount of time that the Earth has been around. And these numbers are just totally unimaginable. The age of the universe is only about 16 billion years, you know, about 10 to the 10th year. So this would be the ages of several of the universes. So you probably don't want to use algorithms that have this kind of running time. Let me sort of dramatize this by plotting pictures here. And the point of this picture, this figure, is that polynomial running times are much more reasonable than these exponential or super exponential kind of running times. On the horizontal axis is n in powers of 2. On the vertical axis are powers of 10, and if we're counting, say, numbers of microseconds. So the number of microseconds in one day is approximately 10 to the 11th. The number of microseconds in 1 century is of the order of 10 to the 15th. So, you know, anytime you use an algorithm that runs more than a polynomial, whose behavior is more than a polynomial, like 2 to the n or n factorial or n to the n, you just cannot solve a problem of reasonable size with algorithms whose running times are something like exponentials or, you know, anything more than a polynomial. So now let me go back to the roadblock problem. We said one way of solving the problem is to look at all the possible configurations, all the possible plays of the game. And as we saw, this is simply not practical. In fact, the roadblock problem does not have an efficient algorithm. We can't prove a lower bound of n to the n, but we can prove a lower bound of at least a constant to the n. There's a constant case such that for every algorithm that solves the roadblock problem, the running time of the algorithm is at least the constant to the n, where n is the number of intersections. So this is an inherently exponential time problem. Any algorithm that solves this problem, any algorithm, no matter how clever you are, you cannot design an algorithm that runs in less than an exponential amount of time. There is no polynomial time algorithm. There's no efficient way of solving the roadblock problem. So even though it's solvable in principle, it is simply not solvable in practice. There is no polynomial time algorithm for the roadblock problem. And this is an example of an infeasible problem. Okay? We find an example of an unsolvable problem. We have an example of a problem that's solvable in principle if you had all the time in the world, or all the time in the universe, all the time in multiple universes. You could solve it, but in practice, it's just not possible. And then the ones that are solvable and feasible are essentially the ones that are solvable in polynomial time. And we'll say for these kinds of problems, there exist efficient algorithms. For me and for the computing, an efficient algorithm is one that runs in an amount of time that's a polynomial, like n squared or n cubed or n fourth. Okay. Well, what about, before I talk about the traveling salesman problem, I want to make sure that you understand the difference between algorithms and problems. There can be efficiently solvable problems for which you design really lousy algorithms. You can have efficient and inefficient algorithms for the same problem. So the sorting problem is a classic problem. You have, say, n integers, and you want to arrange them into increasing order or decreasing order, or it's like alphabetizing, right? Alphabetizing a large list. It's the same kind of problem, putting it in order. And we can think of a really inefficient algorithm for doing this. We could, again, there are n factorial possible permutations of the elements, right? There are n possibilities for the first, n minus 1 for the second, and so on. So you could have a really inefficient algorithm, which is to list all the possible permutations, all the ways of rearranging the inputs. And this would be really, really a stupid thing to do, because it would take too long. N factorial, as we saw, is something that just grows too fast. But it's not hard to think of an efficient way of sorting. say, look down the list and choose the smallest integer, and that becomes your first output. Then you delete that from the list, and from the remainder of the input list, choose the smallest from that, and output that, and continue. So you make n scans through the list. Each time you scan through the list, you inspect in most n elements. So the running time is something like n squared. And we saw that that's a polynomial amount. So this is an efficient algorithm. The sorting problem is a feasible problem. It has an efficient or polynomial time algorithm. And you should note that the sorting problem can, in fact, be solved in n log n time. Anybody know how to do that? You know how to do that. Very good. No. Everybody else has to think about how to do that. Good. Now, what about the traveling salesman problem? Well, the traveling salesman problem, nobody knows whether it's feasible. I don't know. It's not the fact that I'm ignorant or something, but just nobody knows whether there is an efficient algorithm for the traveling salesman problem. And for the last part of the talk, I want to explain the concept of NP completeness. The traveling salesman problem is something that is one of a class of problems called the NP complete problems that are essentially equivalent to each other. And let me give you a quickie definition of what this really means. Because the NP complete problems, in particular the traveling salesman problems, seem to be right on the boundary between what's feasible and what's infeasible. So let me define P to be the class of computational problems that can be solved in a polynomial amount of time. This is what we've been calling the feasible problems so far. And we'll call NP the class of problems whose solutions can be verified in polynomial time. NP means non-deterministic polynomial time. Ideally, the idea is you can guess a solution and check it in a polynomial amount of time. For decision problems, which are yes-no problems, this means the distinction is that for P, these are problems for which you can prove the answer of yes or no in a polynomial amount of time. And NP is the class of problems for which the proof can be checked or verified in a polynomial amount of time. It's the difference really between finding a proof and checking a proof. Now, the traveling salesman problem is in NP in its decision or yes-no version. Given a tour, we can compute its length and check whether its length is at most some input L. The compositeness problem, given an integer, is it a composite number? That is, does it have a factor other than 1 in itself? You can easily check a proof that it's composite. Given the input and a possible factor, you can do long division. Anybody here still do long division? Right? No, you just put it in your calculator, right? Well, the calculator had to do long division. It's a fairly simple, 4th grade algorithm, or 2nd grade algorithm, depending on what kind of school you went to. And you can check whether your input integer is composite. Okay. Now, I want to define the concept of NP completeness because this is something that many of you will see, or you will hear that term. A problem is NP complete if it's in NP, that is this class of problems whose answers can be checked efficiently. And for every problem that's in NP, there's an efficient algorithm for solving it that uses a subroutine for solving the original problem pi naught. So the idea is that suppose you had an efficient way, suppose you had any way of solving pi naught, some algorithm here. Then this problem pi naught is NP complete if you can take any problem in the class NP and reduce it to pi naught in the following sense. You can do some polynomial time computation, and you get an input to pi naught. Say you run an algorithm for pi naught, however long it takes, you get that output, and then you have some more polynomial time computation to get the output for your problem. So this is what we mean by reduce. If you had a way of solving pi naught here, then with some efficient pre-processing and post-processing, you can have a complete algorithm for solving the problem pi. And that's what we mean when we say that it efficiently reduces to pi naught. The idea is if you had a way of solving pi naught, you could solve pi. Oh, I said that. Now notice that if there's an efficient algorithm for pi naught, then there are efficient algorithms for all problems in NP, including all of the other NP complete problems, because for any problem in NP, you'd have if you had an efficient algorithm here, that is a polynomial time algorithm at this point, then the whole thing is a polynomial amount of time, right? Polynomial, polynomial, polynomial. You add them up, it's still a polynomial. So if there's, in some sense, an NP-complete problem like pi naught is the hardest problem in NP. If you could find an efficient algorithm for this problem pi naught, then there would be efficient algorithms for all problems in NP. Okay. That's the key, one of the key characteristics of these problems. Well, the problem is nobody knows how to find whether there exist efficient algorithms for these NP-complete problems. There are many, many NP-complete problems, thousands of problems in all branches of science, engineering, manufacturing, transportation, communications that are NP-complete. Proving theorems is at least NP-complete. Scheduling jobs in factories, scheduling flight crews for airlines, designing integrated circuits, all of these problems are NP-complete. Nobody knows how to solve them efficiently, at least find the best solutions efficiently. No one has ever designed an efficient algorithm for an NP-complete problem, even though thousands of people have tried. So because of this, whenever you have an NP-complete problem, if you can prove that your problem is NP-complete, that's accepted as evidence of its infeasibility, even though we can't mathematically and rigorously prove that there is no efficient algorithm for an NP-complete problem. People accept this as evidence that the problem is really infeasible. It's important to use this argument about NP-complete problems whenever you're asked to find an efficient solution to some computational problem. So suppose your boss asks you, find an efficient algorithm for this problem. And you come back after working very hard, 20 hours a day over 3 weeks, like a graduate student here. Actually, it would be 20 hours a day over 6 years. But anyway, you come back and say, oh, I can't find an efficient algorithm for this problem. I guess I'm just too dumb. Maybe you shouldn't have admitted me to graduate school. It would be better, a better answer would be to say, find an efficient algorithm for this problem because no such algorithm is possible. I can prove that this problem is really unsolvable, or I can prove that this problem is really infeasible. There is no polynomial time algorithm for it. That would be really great. And you know that in some cases you could do that. But the next best thing to proving that it really is unsolvable or infeasible is the following kind of argument. If you can prove that your problem is NP-complete, you can make this argument. I can't find an efficient algorithm. Neither can all these other famous people who've worked on these problems for many, many years. And so surely you can't expect me to find an efficient algorithm for your problem. Of course, your boss may not agree, like that argument, but this is the argument that you can make if you could prove that your problem is NP-complete. So what I've done is build up to the most important research question in all of computer science is, does this class P equal this class NP? Equivalently, is there an efficient algorithm for any NP-complete problem? If P is equal to NP, then since the NP-complete problems are in NP, they are in P, and that means that every NP-complete problem has an efficient algorithm. Conversely, if you could find an efficient algorithm for any one of those thousands of NP-complete problems, there would be efficient algorithms for all of the problems in NP, and that would be, say that NP is the same as P. Now, this problem was posed 25 years ago in this form, although it was known to Kurt Gödel in the 1950s. It was probably known to Archimedes back in the Greeks, but they didn't have this language. But the answer is still unknown 25 years later. If you could answer this question, if you could show that either P is equal to NP or P is not equal to NP, you would be really rich and famous. People would say, you must be really smart. You might win the National Medal of Science. You can't win a Nobel Prize in this field, unfortunately, but you could win some major award. Or at least you could get a PhD at Illinois. I would sign your thesis and say you could get a PhD for solving that question. Okay, so let me summarize here. What we've seen is that computational problems are not all solvable. That, in fact, there are some unsolvable ones, such as the halting problem. Even among the problems that you can solve in principle, there are problems that are inherently infeasible, such as the roadblock problem. There is no efficient way of solving the roadblock problem. There's no efficient algorithm for that. We've seen an example of a feasible problem, the sorting problem, where we could come up with fairly quickly with an efficient algorithm for solving it. And really, we'd like to know what is the boundary between the infeasible problems and the feasible problems. We think the NP-complete problems are right here in this boundary. They're just tantalizingly beyond the reach of feasible algorithms. They appear to be, in some sense, the easiest of the infeasible problems. We think that the boundary is right here, where I've drawn it, that we think that the NP-complete problems are infeasible, that there are no efficient algorithms for the NP-complete problems. But nobody knows. And this is really a great research question, and this question has really driven research in the field for over 25 years now. Let me end by citing my sources. As you know, among academics, plagiarism is the sincerest form of flattery. The cartoons near the end came from this book by Gary and Johnson. The roadblock figure came from this article by Stockmeyer and Chandra. And an excellent source on this subject is David Harrell's book, Algorithmics, The Spirit of Computing. He's written a more recent one, and I unfortunately don't have the citation on me. But if you want to learn more about this subject, you can go to the library and look under the headings computability and computational complexity. Computability is the study of what can be computed in principle, or what is indeed unsolvable. How can we prove that things, computational problems are unsolvable? And computational complexity is really about what is feasible. How complex are your algorithms? How hard is it to solve something among the problems that can be solved? So I'd like to thank you very much for your attention this afternoon. I'll be happy to take questions.
Michael, for a beautiful lecture. Do we have any questions?
You'll probably ask hard questions, Paul.
No. Let me start with one. Oh, no, there. Go ahead, please.
What are some of the unsolvable problems, maybe like in physics, something like that, trying to solve, which would take too much time to do, but
so the question is, what are some problems that appear to be unsolvable in physics? I understand the three-body problem or the four-body problem, given three bodies in arbitrary position and just using, well, maybe they have initial momenta and using the gravity equations, trying to figure out what the trajectories are or whether they will get to a certain final configuration. That one seems to be very complex. I'm not sure whether it's been proved to be NP-complete or whether it's inherently exponential time or something, but it shouldn't be hard to come up with problems, computational problems in physics. Now we're talking about computational problems, which are inherently infeasible or are in fact unsolvable. You know, and we're talking about computational problems, not societal problems like poverty. That's probably unsolvable. But other questions?
How did Turing
come up with this beautiful proof? Well, he was in the right place at the right time. Kurt Gödel, a few years before, had proved that there exist sentences that are true but cannot be proved. So there are sentences, statements about numbers that are true. They are absolutely, without a doubt, true, but there's no mathematical proof of them. And the way that Kurt Gödel's argument went is in a self-referential way. Essentially, Gödel constructed a sentence in logic, you know, using a very formal logical language that said, this sentence is true, but you cannot prove me. Okay, so the sentence literally says, I cannot be proved, and which is true because you can't prove it. So you notice the self-referential. It's this sentence says, this sentence cannot be proved. Notice in Turing's argument, it's you take a program and you give it as input its own text. So there's this, again, the self-referential nature. You're trying to run a program on itself, and that is the genesis of Turing's idea.
More questions?
You might, yes?
Yes. Are there ways of qualifying some of these solutions we call to make it more efficient? Like, for example, the travel and sales, you've got 40 destinations, let's say, the shortest one. possible to say get a solution which is within say 10% of the?
Oh, okay. So the question is, for a problem like traveling salesman problem, is it possible to get a solution that's within 10% of optimum, and so on? Yes, for many NP-complete problems, it is possible to design algorithms that are guaranteed to be no more than 50% worse than the optimal solution. So those are called approximation algorithms or heuristic algorithms, which you've analyzed, and you can prove that their performance is no worse than some factor times the optimal. For traveling salesmen, in fact, that is exactly right. You can provably get within 50% of the optimum. I'm not sure whether there are algorithms that can get you closer. There are, however, other NP-complete problems, so there's a lot of structure here, other problems for which you can prove that there are no, that unless NP equals to NP, there are no approximation algorithms like that. So some of these problems do have good approximation algorithms, some of them do not have good approximation algorithms. And this is, in fact, what happens in practice. You come up with an algorithm that seems to work well in all the cases that you have, and you know it can't, it probably won't give you the optimum all the time, because otherwise you'd solve the P versus NP problem question. But you know you'll come close, and that's generally what you have to do, you know, close enough for government work or something. Okay, is that yes? Yes? So how much more efficiently can you solve the traveling salesman problem? You can do it in order n cubed time, where n is the number of cities, and get within 50% of optimum. Now I said there are n factorial tours, right? So you could do it that way. If you wanted the actual optimum, it is known how to do it in amount of time that's something like 2 to the square root of n. So you actually don't have to look at all the tours. But that's a very deep result from Heldenkarp in the 1960s. But still, just to get the optimum, nothing below exponential is known. Yes?
Using fuzzy logic or anything like that, can they be proven to be solved faster?
So the question is, for fuzzy logic, it has been proved to be faster. It's been demonstrated in a practical sense that it does frequently give you faster ways to control problems than classical ways. However, the use of fuzzy logic is still covered under the theory that we've stated here. Even when I said program or something, or algorithm, a fuzzy logic program is still a kind of algorithm. And it would still have the same characteristics. Now, it happens to be a probabilistic algorithm, at least in most applications of fuzzy logic. And if you prove that your problem is infeasible, requires at least exponential time, deterministically, it still requires at least exponential time in a probabilistic sense. That's known. It's not known whether you could have an efficient probabilistic algorithm for an NP-complete problem. That's not known either. Well, if you find one, that's not quite solving the P versus NP question, but I'll still give you a PhD for that. That's a good result.
Is it also with like exponentially, like if you get within 10% of a problem, like solving it, that might take 2 years, with getting 5% take 50.
Right. You can. There are results like that for specific kinds of algorithms that say, given how close you want to come to the optimum, how long is it going to take as a function of that parameter, how close to the optimum you can. And frequently these approximation algorithms run in an exponential time that's the exponential and the reciprocal of that extra percentage. So it gets harder and harder the closer and closer you want to come. And there's algorithms that are known that have that kind of behavior. Right. Very good intuition there.
We have no further questions. Let's thank Michael very much.
Thank you.